Okay, I guess we'll go ahead and get started here. I apologize for the late notice, but we just found out that Thomas was going to be in town, so we squeezed him in when we could. I understand why we don't have anything to drink outside. Anyway, Tom Chubb, received his bachelor's in science from the University of Sydney and his bachelor in engineering honors the next year. And his bachelor's in science was in mathematics. In engineering was in aeronautical and space from the University of Sydney. He did his doctorate work under Steve Siems and Michael Manton at Monash University on the effect of pollution on precipitation. He's currently a postdoc at Monash University, working on a number of things, including alpine precipitation measurements, weather modifications, and aircraft observations of southern ocean clouds. His previous work with NCAR is he was here in 2009 for the ASP colloquium, and he's been collaborating, of course, with a number of people here, including Jensen and Teresa Campos on this current work on HIPPO observations of southern ocean clouds. He's currently visiting Raoul, and he'll be here through June 7th. So I understand his office is basically upstairs, so feel free to get a hold of him. So with that, let's go with Tom.
Thank you, Stuart, and thanks to everyone who's come along today, and also to anyone who's tuning in on the webcast. I'd like to share with everyone today a piece of work that I and my co-authors have been working on for a little while now, and we're almost at the point of submission. So I'd like to thank my co-authors as well, who have been very supportive in this whole endeavor, and it's been a lot of fun. So let me just get started. So I'm going to start off shortly with an introduction to some of the background on southern ocean clouds. And because I don't really like outline slides, I'm going to dive straight into that. Why are we looking at southern ocean clouds? Well, what I'm showing you here on the left is it's an image from a paper that came out last year, which shows you the model biases in outgoing shortwave radiation at the top of the atmosphere, compared to in the upper left here, the data set used was series. Now there's 22 models here, and also one data set. This is the ISKIP data set here. And the red regions are showing you where there's too little outgoing shortwave radiation in comparison to the data. Blue, where there's too much. What these models in general have in common is that over the Southern Ocean, you see red, okay? And so there is generally too little shortwave radiation leaving the top of the atmosphere.
Not all of them.
Not all of them. There is variability. But this is basically the same thing, averaged. And most of the variability is around the region of 40 to 70 south. And most of the bias is there as well. So these gray lines in this region here are all the ones that have too little outgoing shortwave radiation. What we know is that low cloud regimes dominate the cloud radiative effect at the surface over the Southern Ocean. And there's a number of hypotheses that are currently being investigated to address this. I'm going to talk a little bit about one of them. So we're going to track back in time a fair way to the mid-90s, which was the period where some of the only observational campaigns for Southern Ocean clouds have been conducted. So the Southern Ocean Cloud Experiments, or SOSEX 1 and 2, were intensive flight campaigns that were based out of Hobart in Tasmania in 1994 and 1996. What I'm showing you on the left is data from what they call the baseline flights. And these were flights in which the conditions were deemed to be unaffected by anthropogenic effects. So the wind direction was used to isolate these events from the Australian continental influence. What they found was that in general there were very low cloud condensation nuclei concentrations over the Southern Ocean. And a big seasonal cycle. So in the winter, you'd expect CCN concentrations of about 20 to 50 per cubic centimeter, and 100 to 200 in summer. There's also a seasonal cycle in the cloud droplet number concentration. So you'd expect something like 30 in winter versus about 90 in summer. and correspondingly there was a difference in cloud droplet sizes, so it's not, well, so for similar liquid water contents, there was the difference in sizes. Okay. Now, I also want to talk a little bit about a hypothesis that you're probably familiar with. It's known as the claw hypothesis. It's named after the authors of the 1987 Nature paper, who hypothesized a climate regulation mechanism in which dimethyl sulfide, or DMS, which is produced by phytoplankton productivity in the ocean, undergoes a gas to particle transformation and creates cloud condensation nuclei. Increased concentrations of CCN hypothesized to result in higher cloud albedo, which reduces the radiation received, the shortwave radiation received at the surface, leads to lower surface temperatures and decreases ocean productivity. So this makes it a negative mode of regulation, or a negative feedback. This paper came out around the same time, a little before the SOSEX campaigns. So the results of SOSEX and also another aerosol characterization experiments in the 90s were generally discussed within the framework of the claw hypothesis. And so the figure I'm showing you on the left here is actually from a very recent document called the Socrates White Paper. It's about a possible upcoming major field campaign in the Southern Ocean. Anyway, I liked it because it sort of summarizes some old and new observations of what's going on in the Southern Ocean. So in the dashed line here, it's a long record of CCN observed at Cape Grim in Tasmania at about 40 degrees south. The red line shows you MODIS observations of droplet concentration, and these two black dots with the error bars show you the values from SOSEX, essentially. Now, more recently, the claw hypothesis has come under some scrutiny from the community. There's a relatively recent Nature paper by Quinn and Bates who argue that the sensitivities to each of the steps that I discussed a few moments ago in the claw hypothesis are in fact relatively weak. In particular, the dimethyl sulfide control of CCN concentrations fails to account for alternate cloud condensation nuclei sources. And emissions of sea salt aerosol, or SSA, can increase CCN concentrations by up to 500% above the DMS-derived backgrounds when there are high winds. So one more thing that's come out recently that I just want to talk to you about before I dive into my own work is another climate regulation mechanism. Jorgen et al. Had a paper in 2010 proposing a mechanism for climate regulation through a wind aerosol feedback. So in a warming climate, we expect higher winds in the Southern Ocean. And this is something that's borne out in the observations. And I'll just take a moment to show you on this graphic. This is the wind speed. It's not the anomaly. It's the actual wind speed for about a decade before 1992. And this red belt around here is, well, these are the westerlies, or the storm track in the Southern Ocean. So these winds, as I mentioned, have been confirmed to be increasing observationally. And this leads to, through increased sea spray aerosol production, higher CCN, okay? So this...
What's the scale there?
I'm very sorry about I took this from their paper. So the scale there is -50 to 50 per cc in the CCN.
No, I was looking at wind speed.
Oh, the wind speed? Okay, so the red is 15 meters per second, and blue is 0 meters per second. So this is some sort of mean. The big red patches in the delta CCN are anthropogenic influence. So these are things that are accounted for in their model. But the area over the Southern Ocean is supposed to be from increased sea spray aerosol. the model then correspondingly increases the number concentration of cloud droplets over the Southern Ocean, and there's a negative cloud radiative effect. So this is all sort of model-based, but parameterized by observations of sea spray aerosol fluxes. Okay, so I just wanted to go through those papers to show you that, that there's biases in the Southern Ocean that we're concerned about in climate models. B, it's mostly within clouds. And C, that sea spray aerosol is something that is sort of getting a bit more focus now in the climates and clouds community. Okay, so let's go on to part 2, which is starting to look at flight data from HIPPO. And this is the work that I've been doing with my co-authors. So this is just a graphic showing you some flight paths, okay? I think everybody in this room will be familiar with the HIPPO missions. HIPPO stands for Hyper Pole-to-Pole Observations, and it's a wonderful acronym. Now this campaign performed trace gas and black carbon profiles from the surface to the top of to the tropopause for these global transects. And they performed quite literally hundreds of profiles over 5 different seasons between January 2009 and August 2011. There was cloud physics instrumentation on the aircraft. The primary purpose of this was to basically quality control some of the chemistry data to indicate in-cloud conditions versus out-of-cloud conditions. But as it turns out, it's interesting in its own right and has been the subject of a number of interesting papers in the past couple of years. Just briefly, this is a graphic showing you some of the cloud physics instrumentation on the HIAPER. The ones that I have highlighted here are the ones that I use primarily for this work. So we're looking at the ultra-high sensitivity aerosol spectrometer, which measures aerosols between 0.06 and 1 micron in 100 bins, and the cloud droplet probe, which identifies cloud droplets, again in 30 bins between 2 and 50 microns. These other instruments have been useful in various ways for sort of quality control or other checks on the data. Now, I started looking at the Southern Ocean data with a view to performing some sort of a climatology of number concentration in the northern southern hemispheres. And very early on, this graphic struck me. The first image on the left is from a flight performed in April of 2010, and the graphic on the right is a flight in June of 2009. I noticed that there was a really big difference basically in number concentration, and I started asking questions why. By the way, the graphic on the left I suppose to be more typical of Southern Ocean conditions. The graphic on the right seemed high, which is why I started looking at it more closely. So the question that I was asking was, what was the cause of the high number concentration in these clouds in HIPPO 4 RFO6? The cloud condensation nuclei concentration must be well above the expected values for the Southern Ocean. And that's about 50 per cubic centimeter. And fundamentally, I identified 2 competing hypotheses to explain this. Number one is that there had been long-range transport of aerosol from the Australian continents, and that's about 1,000 miles in this case. Unfortunately, there weren't any observations of aerosol composition, apart from black carbon on the soot photometer. So in this talk, we're going to look at back trajectories, UHSAS concentration, and trace gases to evaluate this hypothesis. The other hypothesis is that there was elevated local production of CCN in the form of sea salt aerosol, as I've been sort of going over in the introduction. And what we know is that this has been sort of an idea that's been around for a while. Woodcock in 1953 found a monotonic increase in SSA concentration with wind speed. But more recently in vocals, blotted owl didn't really see this, but they really only looked at wind speeds up to about 15 meters per second. And Lewis and Schwartz identified two distinct mechanisms for SSA production. One is bubble bursting in little breaking wavelets for lower wind speeds, and spume production, which is where droplets are torn directly from the crests of waves in higher wind speeds. Okay, so this is the flight that we're going to be looking at in some detail from Christchurch to Hobart on the 29th of June in 2011. Wind speeds I show in green shades here. Pressure contours are in gray. There are some temperature contours in red. And I've got the Bureau of Meteorology frontal analyses overlaid on all of this. So it's a fairly strong frontal passage. You've got these high wind speeds into which the HIAPER really did fly. And you've got an area of fairly strong warm advection. Okay, so to sort of zoom in and give you a little bit more detail, there are three panels here. The first one is cloud top temperature from the MODIS instrument, which happened to pass over in the middle of the flight. And I've indicated the positions of 4 profiles. Now, I've done them in reverse order for reasons that will become apparent. So profile 1 was actually the last profile performed. So the cloud top temperatures in these boundary layer clouds that are sort of ubiquitous in this image are a couple of degrees above zero. So these low clouds are all warm. The blue cloud overlying everything here is the frontal band. It's actually, it looks big and thick, but it's actually not particularly deep cloud. And there's some mid-level cloud you can identify as well in these green colors, which is, as it turns out, it's predominantly supercool liquid water cloud at about -15 to -20 degrees. The middle panel is the effective diameter parameter derived from MODIS. I've masked out in light gray where there's ice, and in dark gray where the solar zenith angle was just too low so to make any retrieval. And the final panel is some processing I've done myself, where we get number concentration of cloud droplets using the effective diameter and the optical thickness of the clouds. And the table below does some comparisons. Now, one thing you should be aware of is that, especially to the south here, the solar zenith angle is still quite low, so I don't have particularly great faith in the exact values of the retrievals. But I wanted to point out that basically when the number concentration measured by the CDP is high, so is the number concentration from MODIS and vice versa. I have a bit more faith in the values in these boxes up here, which are boxes 4 and 5, so the top row of the panel, which has NC from MODIS at about 150. Okay. Now to get to the profiles themselves. These are just some images taken from the forward-facing camera of the aircraft for profiles 1 and 2. And what we see, essentially, we're looking down at boundary layer stratocumulus cloud. In both of these profiles, things are on a broad scale, fairly homogeneous. But if you look closely, you can see that there's kind of microscale heterogeneity. You can see that there's, outlines of individual cells going on and that sort of thing. So it's kind of, there's sort of what you might expect to see. The overlying cloud in profile 2 is very high. It's at about 8,000 meters. And it doesn't really have any influence on what we're seeing here. Now, these profiles are showing us some of the vertical structure for profiles 1 and 2. The first panel is showing you virtual potential temperature, just to give you an idea of where the inversion is. So you can see that both of these profiles have a capping inversion at about 1,200 meters. The first profile, which I show in black, I'll just take a moment, I'm sorry. I wanted to show you something about these legends first. I'm showing you an offset for each of the lines. So if there's an offset of +10, what that means is that I've moved the line to the right by 10 units in order to make the comparisons a bit more clear. So there's not a difference of 10 degrees between these profiles. Now, profile 1, I tend to classify as being a relatively classic profile. So you've got pretty much adiabatic liquid water content, strong capping inversion, and sort of average wind speeds of about 15 meters per second and relatively low shear. What we have in terms of droplet concentration through this profile, it has a mean of about 63 per centimeter cubed. And the particle size on the CDP increases with cloud height. And so this corresponds to all we think we know about stratocumulus layers. The final panel over here shows you the UHSAS concentration, and I've masked it out where it's in cloud with this dashed line, because we had some concerns about splashing of drops on the inlet affecting the results, and that's why we think we see a very large spike here. Profile number 2 is a little bit more complex. It's slightly different. We don't have the same adiabatic profile through the entire cloud, but near cloud top it does follow that line. Lower down in cloud, it's relatively constant with height. One of the most interesting things about this profile in terms of its structure is that there is an entrainment layer, a mixing layer of about 200 meters deep above cloud top before this final inversion here. So you see that in the difference between where the wind shear starts to increase and where the cloud top is here. It's about 200 meters. Otherwise, it's relatively similar. The wind speeds are a little higher, and the droplet concentration is about 100 per cubic centimeter. Remember, there's an offset of 100 here in this graph. Also in cloud, I've masked out the number concentration of aerosols, but below cloud we get results that agree well with the in-crowd droplet concentration. Okay, so this slide is mostly just to make sure that I said everything I needed to say in the previous slide, and also so that the webcast can go back over it. But basically, we have two profiles that are relatively easy to understand in terms of our understanding of maritime boundary layer structure. Profile 2, as I said, was a bit more complex, but the intermediate layer has been identified in a number of publications before, so it's well enough understood. Now, profiles 3 and 4 are a little different again, but I look at them together. So you can see straight away from the camera images that things are not nearly as homogeneous as profiles 1 and 2. We haven't really got the nice flat cloud tops that we saw previously. And there's definitely more spatial heterogeneity in terms of the cloud field. In terms of the cloud structure, one thing that we noticed straight away is that the cloud liquid water content is very far from being adiabatic, and the maximum liquid water content is nowhere near the tops of these clouds. The wind speeds are a lot higher in both of these profiles, so they're 25 meters per second at the lowest level the aircraft reached, which was about 160 meters above sea level. And there's quite a lot of wind shear, both directional and in terms of speed. The number concentrations were on the order of about 200 per cubic centimeter. And I should just mention that I've been quite strict with what I term cloud. It needs to be at least 0.05 grams per meter cubed of liquid water. And the UHSAS concentrations are high as well. You can see that I've masked out a lot of this for fear of contamination by liquid water, but we've actually spent a good deal of time looking at the cloud droplet sizes to ensure that splashing is not too great of a problem. Okay, so to recap that, very much non-classical boundary layer structure in these profiles, in high wind speed and high vertical shear. Cloud droplet concentrations were much higher than we would expect for the Southern Ocean for both of these. So for profile number 3, it was up to 250 per centimeter cubed at the bottom of the cloud. And for profile number 4, the average value was 188 per centimeter cubed. But due to some spatial heterogeneity, I'm worried that this might be undersampling a little bit. So if you use a higher liquid water threshold, to rule out periods where maybe you've sampled some cloud and some clear air, you can get values up to 400 per cubic centimeter. And this corresponded better with the values of aerosol concentrations at and below the cloud, at the bottom of the cloud. Okay, so that's a summary of the observations in flight. I now want to try and address the hypothesis that pollution may have been transported from the Australian continent to very far into the Southern Ocean and be causing the elevated NC and NU in these clouds. Now, long-range transport of aerosol has been identified over the Southern Ocean. Downey et al. Detected episodes of continental air incursion on Macquarie Island by looking at radon concentrations as well as condensation nuclei. And what they found was that for there to be a significant impact on the CN counts, really a direct hit on a pollution source was required. So the image that I'm showing you here is some back trajectory analysis they did. The solid line along the bottom is the number of hours of contact with the continental landmass that these trajectories had, and the line above is the CN concentrations. So you'll see that in some cases there's very, very good correspondence between contact with land and CN concentration, and in other cases there's very little impact at all. So these are where point sources such as the Melbourne urban centre or other industrial areas have been implicated in the MS history. Now, to evaluate whether the observations that we saw in and around the clouds were due to continental pollution, we're going to look at some additional data that was collected on the HIAPER during this flight. And namely, we're looking at carbon monoxide, black carbon, and also profiles of UHSAS concentration. Now, carbon monoxide and black carbon are very good indicators of anthropogenic activity because they're products of combustion. And there were 4 CEO instruments available on HIPPO4. We're using the vacuum ultraviolet resonance fluorescence instrument. And we're going to use the soot photometer for black carbon. Additionally, we use back trajectories to associate the observations at different altitudes with possible source locations. And for that, I ran high split on the global data assimilation system, which is a 0.5 degree resolution product available 3-hourly. And in order to sort of characterize the uncertainty with these back trajectories over a long distance in a data poor area, I've run ensembles with perturbed initial positions to create 27-member groups. Now, to look back at profile 1, which we can remember was the classical profile, I'm again showing you a profile of potential temperature, but this time we're going much higher, so we're going all the way to 8,000 meters. So the clouds are down in this region here, but I wanted to look at long-range transport in more of the troposphere. The second panel is carbon monoxide. You can see there's a little bit of missing data here. Third panel is black carbon, and in this profile there was barely any black carbon registered. And the fourth panel is my UHSAS concentration again. One thing that you'll notice is then that in most of the troposphere, these concentrations are quite low, and that's really typical for the Southern Ocean. It contrasts quite strongly with some of the North Pacific data that I've seen. This feature that I'm pointing out in the blue lines, which correspond to the 3,000 meter trajectories, is a possible influence in the carbon monoxide profile. And it may correspond to a slight increase in number concentration of aerosols at the same height. They seem to be somewhat correlated. But there's really no source that you can pin them to with any of the ensemble members not passing over land at all. These lower areas show you it's very, very clean air just above the boundary layer with number concentrations of around 10 per cubic centimeter. And within the boundary layer, you've got the values that I stated earlier of around about 70 or 80, up to 70 or 80 in the lowest levels of flight. Profile 2 is a bit more interesting. This is probably the profile in which signals of anthropogenic influence are most evident. Here at about 4,500 meters, you can see that there's highly correlated carbon monoxide and black carbon, but there's no signal at all in the number concentration of aerosols. And I can't quite fully explain that yet, but I wanted to point down a little lower at around 1,500 meters, where you see there is a correspondence between number concentration of aerosols, black carbon, and carbon monoxide just above the top of the boundary layer. And that green set of trajectories passes over the continent, and it just so happens that this region here is quite well known for industrial activity. In fact, it featured in Danny Rosenfeld's 2000 science paper looking at the effects of pollution from that region on precipitation in the Snowy Mountains. So it's certainly been implicated as a pollution source before. Moving on to profile 3, just to confuse you, I've added some more profiles here. So the dashed lines are now the ascending profiles that are in approximately the same area. The reason I did that is because there's some missing data from the black carbon in sort of a critical area, and I wanted to highlight it. So it would seem that around 2,000 meters, there's another bit of a continental incursion going on above the boundary layer, because there's a correspondence between the black carbon and the number concentration in the ascending profile. There's not really a signal. There's maybe a weak signal in the carbon monoxide. Now, I should just mention that there's in this profile number 3, there's quite a divergence in the air mass history. So you can see that for each of the levels, the ensemble becomes split. And basically, that's because the perturbed initial conditions straddle the region of the cold front. So it's a convergence line, and trajectories that started ahead of the cold front end up somewhere around the continent, and trajectories that started behind the cold front end up over the Southern Ocean. So you can trace this incursion at about 2,000 meters back to the continent here. If you look at this green set of trajectories here, they're low over the continent at about 30 hours prior to the profile being performed, which sort of adds up. On the other hand, in the area, in the boundary layer, there's no signal in the carbon monoxide at all, but there's a very large increase in the number concentration of aerosols. Droplet splashing as a possibility notwithstanding in this case. And in profile number 4, the clearest evidence of any influence, if there is any at all, is quite high. It's at about 4,000 meters, okay? And you can link that back to a trajectory that passes over the continent over here. Unfortunately, there's very little black carbon data, but you can see that there is a correspondence between increased carbon monoxide and increased aerosol concentrations. At 1,500 meters, the air looks very, very clean, with almost 0 aerosol concentrations and carbon monoxide at about 50 parts per billion volume. And in the boundary layer, with a very, very slight increase in carbon monoxide, we see an increase in aerosol concentrations of a factor of about, well, a very large factor. It's gone from 0 above the boundary layer to at least 400 within the boundary layer. And just to kind of put some context on these numbers, this slide is showing you some data taken from a flight several days later. It's RF-07 of the same campaign, and it was performed, well, these profiles were performed to the north of Tasmania, directly in the pollution plume from Melbourne, okay? It's about 100 miles south of Melbourne, and what you see is massive increases in the number concentration of aerosols to above about 2,000 per cubic centimeter, and corresponding large increases in carbon monoxide and black carbon. And the reason I'm including this slide is essentially to hammer home what a polluted plume really looks like in terms of these observations. Okay, so to summarize this work on the pollution transport analysis, none of these profiles were 100% pristine, and that would have made this really open and closed, but it's much more interesting this way. But each time there was an increase in the aerosol concentration in the free troposphere, we could associate it with either black carbon or carbon monoxide. Now, profile 1, in spite of being the closest to the continent, was probably the cleanest of all of the profiles that were done. And we found in that case that aerosol concentrations and cloud droplet concentrations match the climatological values fairly closely. Profile 2 was the most polluted and could be readily associated with a pollution source, but the boundary layer number concentration of aerosols was only really slightly elevated above what you'd expect for the Southern Ocean. Profile 3 had a signal in aerosol concentration above the boundary layer that could be associated with black carbon and carbon monoxide. But what we found in that profile was that the signal for aerosol concentration was 5 times as big for a smallest carbon monoxide increase. But as I said, we do have some concerns about droplet splashing on the UHSAS. Profile 4, we have no such concerns because we're satisfied that the droplets at the bottom of that cloud are small enough not to affect the data. And it was in this cloud that we found the highest aerosol concentrations and the highest cloud droplet concentrations. And there was low carbon monoxide. And in general, it was a fairly clean profile. So just to go back to sea salt aerosol production, there is a growing body of literature that supporting that sea salt aerosol is important for CCN concentrations in the remote oceans. But there's still some ambiguity in the theory of production and in the observations themselves. Really high wind speeds were experienced in the boundary layer for profiles 3 and 4 of about 20 to 30 meters per second. But actually for the Southern Ocean, this isn't spectacular at all. You'd find that within the region of a cold front quite frequently. Additionally, most of the sea salt aerosol observations have been done in lower wind speeds, so you don't necessarily see this increase at these lower wind speeds because we wonder if there's some criticality in the sea salt aerosol production of wind speeds of about 20 meters per second. Okay, so to summarize what I've done here, we found a 4 to 5-fold increase in cloud droplet concentrations and aerosol concentrations between profiles 1, clean, and classic, and profile 4, which is also, we suppose, clean, but quite non-classic in this high wind and high shear environment. We were able to rule out pollution as the main cause of this increase in aerosol concentration, and we attribute it primarily to sea salt aerosol fluxes in high winds. Now, our findings seem to verify the link between increased wind speeds and number concentration of cloud droplets over the Southern Ocean, as hypothesized by Jorgen in the wind aerosol feedback mechanism I discussed earlier. The mechanism is consistent with his work because we observed a corresponding increase in aerosol concentration as well. Just so happens that it was exactly in the same spot as Jorgen noted in the maps I showed you earlier, but that's probably just a chance thing. As I said, not all of the previous work identifies a monotonic increase in sea salt aerosol flux with wind. For example, the vocals paper I mentioned. And I'd like to know if there are other factors we should be exploring. And an area of research that's ongoing at the moment is the impact of sea surface temperatures on sea salt aerosols. And what we really need is more observations of sea salt aerosols directly in terms of composition in high wind conditions. And maybe that's something that can come out of Socrates in a few years. Okay, and that's my list of references. Thank you, everyone, for coming along. And if you have any questions, I'll take them now.
Okay, thank you, Tom. Do we have any questions? I'm sure we do. There we go.
Thanks for the presentation. For the figure that you showed, there's a correlation or there's a higher concentration for black carbon CO, but you didn't see a correlation with aerosol. I wonder if you think that will be related with aviation activity?
I've considered that possibility. This region is a very low traffic area for aviation. There are very few flights to the south of Melbourne that could have caused this.
Yeah, and what is your comment on the other figure that doesn't have a correlation between CO and black carbon? Any any suggestions on the reason why?
I'm sorry, was that
This is, yeah, probably profile 3.
profile 3? Yeah. Okay, so there's no carbon monoxide, but there is black carbon and number concentration. That's difficult to evaluate, actually, and I need to discuss this more with my co-authors. You would expect, of all those variables, the best correlated would be CO and black carbon. And if there had been any precipitation, it would be the black carbon and the aerosols that would disappear, and not the carbon monoxide. So I haven't quite got to the bottom of that one either.
Thank you.
So did you look at the size distribution of the aerosols? I'm thinking that sea salt has a different signature than pollution, maybe.
I have looked at the size distribution. There's not a massive difference in the shape of it. There's more of a difference if you look above and below the cloud, actually. So there's some in-cloud processing going on with these aerosols, but between the different profiles, they can be quite similar.
Any further questions? No? Well, let's thank Tom for his seminar. And like I said, he'll be here through June 7th.
Thank you.